Thank you very much for coming. I'm quite happy that there are people in the room. Today I'm going to talk about the application of recurrent neural network to innovative drug design. So I'm going to go through some basic things about the recurrent neural network in the context of drug design, in the context of molecule, chemical species generation. Let's go through the agenda. First, I would like to say a few words about who am I. Then we'll go through the recurrent neural network, some quite general introduction, some equations as well. Then I'd like to go through some generative approach in natural language processing, just to draw at the analogy between standard language generation and molecules generation. So I'm hoping that at the end you will see this connection between these two worlds. Then a few slides about the recurrent neural networks in chemistry. And the final part, the use case of molecule generations. So I'm going to go through the SMILES codes, and I will introduce the SMILES representation of chemical molecule. Then a few words about the Python cheminformatics libraries, and then we will be generating the molecules, hopefully some drugs. And then at the end, the summary. So, who am I? I am a chemist, actually. I come from natural sciences. I've done my PhD in Karlsruhe in Germany some years ago. Now, currently, I am a competence center manager at PSI Polska in Poznań, where I lead a team of advanced methodologies, a team of analysts. We apply a lot of machine learning for industry problems like time series forecasting, predictive maintenance, predictive quality, prescriptive maintenance, and so on. Also the multi-criteria optimization, fuzzy logic, and other advanced analytics. And I also work for Polish Academy of Sciences, where I am actually trying to apply the recurrent neural network for drug design, which is the topic of today's presentation. Also molecular docking and quantum computational chemistry. So let's go through. First, I'd like to show this tweet. This is François Chollet, who is the inventor of Keras. He is very pessimistic, actually, about AI, and I tend not to overuse the term artificial intelligence. I don't think that the algorithmics we have now, it's intelligence in the human being sense. I would say this is just advanced algorithmics. So let's have this in mind. This is just my, let's say, also my point of view. The recurrent neural network, just a few thoughts. The human being brain usually does not learn a single isolated information. Usually we have some sort of context around. And the recurrent neural network is designed in such a way that is capable of capturing the context. The hidden layer, which I'm going to introduce soon, is responsible for catching this context. One can consider actually, when thinking about recurrent neural networks, what various time steps. The time series might be, let's say, a prototype, a very basic object that is actually can be the subject of the application of recurrent neural network. Now I'm using a Jupyter Notebook with Riese. This is a plugin to Jupyter Notebook which allows on the execution of some scripts. So we are going to execute some scripts actually during this talk. This is a time series, a simple time series where we have meteorological conditions like temperature, pressure. This might be also humidity, precipitation, or other things. Just a time series, and actually the recurrent neural network is very, very capable of capturing the knowledge which is embedded in time series, and then we can stimulate, for example, this recurrent neural network to produce new species of the same kind, the next available at this time time step with expected quantities, which is something like a forecasting. So they are very good algorithms for forecasting of time series. What is the structure of RNN? I will go very quickly through some equations. So we have the, as usually in deep learning, we have a couple of layers. The output layer contains couple of units, which means that we can predict the sequence. So the key point is that we can introduce to recurrent neural network the sequence, and at the output layer we can also get the sequence. It's computed in the following way. By the way, we have do we have the laser pointer? Do we have the laser pointer? No. Fine. So we have this WHO, which is the output connection matrix, the hidden state, which I will be showing on the next slide, and then the bias of output layer. And as usual, we apply the activation function, hyperbolic tangent or something like this, to get the final response of our neural network when doing a forward pass. Yeah, so the mysterious thing, which is not available in, let's say, multi-layer perceptron, is this hidden layer. And the hidden layer is defined so in this way, this HT equals FH applied to OT. So you can see that we have additional activation function in addition to the one we saw at the previous slide. We have this OT, which is just the standard matrix connecting the input. XT is the input. These are our predictors, the data we introduce to the network. So we have an additional matrix WHH, which is applied to the HT-1, which is actually the previous hidden layer. So we have to know this hidden layer at the time step T. We have to know the hidden layer from the previous time step. Yeah, we have an additional hidden layer activation function. And the input layer is just the layer through which we introduce the data. So, for example, like in this time series, we had two predictors or two quantities, like temperature and pressure. Then we can imagine that we have just two input nodes through which we introduce the sequences. And this is important in the context of a recurrent neural network, that we introduce the sequences. Like in the multi-layer perceptron, we usually, let's say, introduce the single time step, and we don't have, we are not able to capture the context, which means the time steps which are around. So in the case of recurrent neural network, we introduce entire sequence, and at the end also we can get the sequence as a prediction. So I'm not going to spend too much time on this, so I repeat this equation here. We have the connection to hidden layers. So when we introduce the predictors, then we, instead of going to, let's say, the next layer, we have something like an intermediate layer, which is this hidden layer, which is actually responsible for capturing the context information. Yeah, and then for this we have the matrix of hidden states, this WHH, yeah, as you saw in the previous slides, applied on to the hidden state of the previous time step. And as usually we have the bias, which we apply as an additive component. The key equations, so in the bottom, in the top we have the output layer, so this is the, let's say, the very end of our forward pass, so this is the YT is the prediction. In the middle, we have the hidden layer, which is applied to the OT. I mean, it's just the outcome of the application of hidden layer activation function to the OT, which has been defined before. And yeah, and also here. So a couple of equations just to see this, some graphical representation. We have. Here this incoming predictors, like quantities we want to introduce to the network, and then we have hidden layer with all these quantities or matrices which are needed, like this WHH, and at the end we have the outcoming layer, the output layer, where we get the predictions. The training process is, as usual, we have the loss function where which measures the error between the real responses and the predicted responses. And as usually, we just calculate Yeah, we use the standard gradient descent approach, where we have to calculate the first derivative of our loss function with respect to the network parameters, which are the components of the matrices. And we have the generalization of backpropagation, which is called the backpropagation through time, because we have to iterate over the time. And this is a problem because we have some problems and issues associated with recurrent neural networks. So if we consider this the simplest possible recurrent neural network, which is called vanilla recurrent neural network, the one I've actually shown, the equations, then we have the vanishing gradient problem or exploding gradient problem. This is sort of a numerical instabilities associated with the learning process. And there are quite a few recipes to go around these problems, like a more heuristic approach to optimization, to putting some boundaries on the network matrices, but these are actually some patchworks. So in principle, the standard vanilla recurrent neural network is not used that often these days. We have the LSTM, the long short-term memory unit, which is actually applied more often. I will not go through the slide in detail. We have a lot more matrices and a lot of network parameters. We introduce our predictors, our incoming quantities in a couple of places, but as before, we have the hidden state and we have the prediction, the output layer. Let's not go through this math in detail. The thing is, or the important message is that here we the application of LSTM actually alleviates the problem with vanishing or exploiting gradients. And the demos I will be showing, they are actually based on LSTM, the LSTM-based neural network. So first, I would like to show the recurrent neural network applied to the natural language processing in the, let's say, generative context. So we'll be generating some statements. Well, I've taken, not myself, I found on the internet the set of 32,000 tweets of current president of the United States. And I found also on the internet the predictive model which has been trained on these tweets. And we'll be, in a few slides, we'll be somehow watching how the neural network is producing the tweets. So we have like a 3 megabytes of text, which is like 3.1 million of characters. The dictionary contains 98 characters, upper, lower case digits. We know that we have the special characters in Twitter, like the hashtag or the mentions. And the network has been designed in such a way that we've been cutting the pieces of 60 characters and introducing these batches, these pieces, into the neural network as predictors, and the next character was the outcome. So we will see in a second how this look like in practice. In a way, I would like to encourage you also to do the data science in Dockerized environment. I will not go through in detail through this one, but the architecture or the presentation you see now is based on Dockerized environment built from Jupyter Notebook and Minio. Minio is a private cloud used to withdraw the files. Okay, so let's go through the code. So I'm going to load the tweets. So we have the tweet data in the tweet data variable. And yeah, this looks more or less like this. So these are all the tweets combined, one after another. Yeah, the learning process looks like this, that we have 60 characters long pieces of the tweet, and this is the predictor, of obviously one hot encoded, and the next character is just the response. So we more or less train the network in such a way that we want to predict the next character. Altogether, we have something like 3 million long training set. And yeah, what I'm going to do now is I'm going to create the neural network, recurrent neural network architecture. I use Keras with TensorFlow backend here. And actually, yeah, this is the vocabulary, the entire set of characters. And this is the network, like four layers of LSTM-based units, 512 nodes per each layer. At the end, we have the activation function as a softmax, and categorical entropy as a loss function, actually. This happens. So the model summary is the following. So we have these 4 layers of LSTM nodes, and which altogether means that we have 7,600,000 network parameters to be optimized. So this is a non-trivial optimization task to optimize this. But this works. So I'm just loading now the previously trained model, which I found on the internet. A couple of slides before, I've provided the GitHub link to this repository where you can just take it and do it by yourself. Some helper functions, and we are going to predict. So we are going to do generative machine learning. So now the previously trained on the Twitter dataset neural network is now producing new data. So the seed is just the incoming seed of the tweet, and then the rest is done by the neural network. So you can see that somehow we have incorporated properly the syntactic part of English language. Yeah, and also you can see that all these things, like special features of Twitter, has also been introduced to the network. So the mentions and the hashtags are used, so it looks like a tweet. One can have, let's say, doubts whether this makes sense or not. Sometimes the statements are, I would say, surprising. Sometimes they doesn't make sense. But in principle, I think, yeah, we have incorporated the syntax and also, to some extent, the semantics of English language. Yeah, so more or less the summary of this part is here. The important thing is that the generated entities have the features of real tweets, like these mentions and hashtags. This is important because now we'll switch to the chemistry, and you will see that the language I'll be incorporating to the recurrent neural network, the language of molecules, is also quite specific. So the recurrent neural network in chemistry, molecular generation. So what's the SMILES code? The SMILES code is just the character representation of molecules. I'm going to show in a few slides a couple of examples how this looks like. This, from mathematical point of view, the molecule by itself is just an undirected graph where the nodes are the atoms and the edges are chemical bonds. Yeah, and the SMILE specification is capable of storing simplified information about the molecules as a string of characters. In fact, the molecule is a three-dimensional species, so one can imagine that if we just take if we turn the molecule into just this string of characters, then we'll obviously lose some information. SMILE is quite mature. It supports, for example, stereochemistry of chiral compounds. So it is, well, I would say mature solution, mature specification. You can see here just we have some molecule, and actually what we do is we remove the hydrogen, the light atoms, and what we do is we simply, by using an algorithm, turn the order of heavy atoms like nitrogen, carbon, carbon, nitrogen, and so on, in a string of characters. Obviously, there are rings, so we have the parentheses to reflect the ring in the SMILES code. Altogether, one is able to turn each molecule, even the most complicated piece of DNA, or I don't know, the some lipids or proteins into a string of characters. We can have a look at the example. So, for example, one of the simplest molecule one can imagine is water. As I mentioned, we don't put here the hydrogens. The hydrogens are redundant. So the Smiles code of water is just O. And then if we instantiate the molecule from the Smiles code, we'll magically see the H2O, which is water. There are more complicated things. Methane, CH4, we don't put the hydrogens. They are implicitly somehow contained. Even more complicated, like butane, four carbon atoms and a couple of 10 hydrogen atoms, and so on and so on. So here we have not a linear form of butane, but this is methyl isopropane. Everything can be done via Smiles coding. Hexane, similar, and then we have more complicated and unsaturated compound. Yeah, again, the double bonds is just introduced by equal sign. And the rings, so we put number 1 here, and then magically cyclohexane appears. Yeah, and the benzene, the simplest possible aromatic compound, can be also introduced in the form of Smiles code. Something more difficult, more complicated, more complex, ibuprofen. Yeah, here I didn't put the hydrogens. So in the previous slides you could see that there is this add HS function. By the way, I'm using here some cheminformatics library to do all these things. I have to speed up a little bit because I don't have a lot of time. The ibuprofen was there, the caffeine. We have a lot of caffeine over here, and here also we have some caffeine, again, and instantiated from just a Smiles code. So the stereochemistry, I don't know if you remember from organic chemistry what is the stereochemistry. Yeah, sometimes we have two molecules and they are created in such a way that their mirror reflections are, it's impossible to put one molecule onto another molecule if we consider two mirror reflections of these molecules. And as you can see here, the stereochemistry, the S or R absolute configuration can be introduced via this sign. So you can see here that here we got the fluorine above the plane of, let's say, screen, and in this case we have the fluorine behind the plane of screen, which exactly means that these are different stereoisomers. So Smiles is mature, Smiles is capable of doing a lot of things. Yeah, also the cheminformatics libraries, they allow to calculate some molecular descriptors like molecular weight, the molecular weight of heavy atoms. So here we have CH4, we have one heavy atom, which is carbon, with a mass 12 atomic units, number of valence electron 8. There are a lot of other capabilities. This is just an example how one can use Python for chemistry. Yeah, we have at least two important libraries like OpenBabel and RDKit. Both of them are used within this study. Both of them are open source, and they are very, very, I would say, friendly to the scientist, as Python is quite friendly to the scientist. The generation of new molecules, I've taken the database of chemical molecules, 13.5 gigabytes. This is the ChemBL library. It is 1,800,000 distinct molecules. Some of them have biological activeness. Well, it will not go through the nature of this let's say of this term. But this is IC50. This is a measure of the potency of a substance to inhibit some specific biological or biochemical function. So it means that if we introduce this compound to human or animal body, then something will happen. Actually, it's not neutral. the molecules, yeah, so I've taken just 500,000 of these molecules with non-zero IC50. I've turned these molecules into the SMILES codes, and I've processed them into the canonical form. And actually what I did is I've introduced exactly the same approach which has been introduced for this natural language processing. I've combined all the molecules into one very long string, and I have converged the LSTM-based recurrent neural network. So I have optimized this recurrent neural network on this data set, and then I've been stimulating the network to produce new molecules. So we'll see this actually right now. Yeah, I've applied standard software like a TensorFlow, Keras, these two mentioned libraries, also some data persistence layer, database persistence layer like SQLite, Postgres, and other Python ecosystem to pre-process the data. There are some existing references, so people are actually doing research of this sort. So let's go through this prediction. I have only 4 minutes to do this. I'm just taking now this, and this might take a minute or something like this, the data set of these molecules from Minio, actually, from this private Dockerized cloud. It's already in, so this is the CSV file with the molecules, so you can see that there are SMILES codes and some other, let's say, descriptors of the molecule, like number of rings, element set, and so on and so on. The standard mean, the last column is, by the way, this IC50, the standard, the mean value of IC50. Okay, so the molecules look like this, actually, some randomly chosen molecules from this data set. So again, you can see that these cheminformatics libraries, they provide also the capabilities of visualizing the molecules. Yeah, and then here we have the architecture of neural networks. So I'm just now incorporating the model, the previously trained by myself model, which will be used in a few slides or 1 or 2 slides to predict new molecules. Some vectorization is taking place, so this might take a while. Yeah, we'll see in the next slide the the training has been done on high-performance computing computational center. It took quite a lot of time to converge this predictive model. Yeah, I've received 80 till 55% of accuracy, depending on the attempt. Yeah, and the important thing is that in such a non-trivial optimization of neural network, one has to put a particular attention of learning rate. So I've applied some heuristic approach to manage the learning rate because otherwise the network does not converge. So similar to the previous case, this is just my set of characters, set of string, set of SMILES codes. As you can see here, there is from time to time Q, or this is maybe before putting a Q. No, there is a Q. The Q is just the separator. So Q means that the molecules has just ended and the next molecule is going to start. It's important during the prediction phase because we will be awaiting for the Q just to finish the current molecule. Yeah, and similarly to the previous case, the predictor is just a sequence of given size, given length, like 40, and the next let's say, character in the string is just the target. So in this way, the predictive model has been trained. Of course, we have to one-hot encode the atoms. So the C in a sequence of characters is just a vector, the binary vector with just one non-false field. Yeah, altogether the neural net model is a bit smaller than the one before, but again I've created this from LSTM units. The prediction phase is exactly the same as before, so we introduce some sort of seed and then we await. Well, we predict the next molecules and we await for a Q. Which is just the very end of the molecule. Yeah, and then I've done also some post processing of these molecules to get the 3D object. So let's go through. So now we are predicting that this is a seed, and we are predicting 2,000 characters long string with supposedly new molecules. So this might also take a couple of seconds. I'm already after my time, but we have just, let's say, 1 or 2 minutes. So I've just created this 2,000 characters long string, and I have cut the string into molecules just by having this Q as a separator. So we've got something like a 73% of correctly predicted smiles molecules. They look like this, actually. So these are new molecules, some new quality which just appeared from the previously trained recurrent neural network. They look like this. This is some cleaning, and we can have a look at them. So these are these new molecules for being so fast, but I am out of time at the moment. Yeah, so this I'll skip. I will not have time. So I like to go to the summary. So I've introduced the recurrent neural network. I've also introduced the natural language processing, funny but important use case. Then I've been talking about the smiles codes and the cheminformtics libraries. Yeah, the LSTM-based neural network learned properly the syntax of smiles code, and I'm hoping that yeah, this is a superior assumption that together with this syntax knowledge, also the semantics, I mean this biological activeness, the fact that in the training set I had the biologically active molecules has also been incorporated into the recurrent neural network. Significant fraction of generated smiles codes are reasonable, chemically correct molecules. Some of them in the statistical analysis turned out that they are the repeated species from the training set. I have some more research on the way, and that's it. Thank you very much. Thank you very much for coming, and thanks for your attention.